Okay, and so this is our last How Are We Doing assignment that I wanted to make specifically on questions that students had from this last assignment. And so there weren't too many questions, but there were a few things that I just want to review from a few of the questions that were presented. So the first thing was understanding which F value table to use. So there are F value tables in Canvas. And the student mentioned that some of the values may be different than the online ones that I've used in my videos. So in Canvas, there is a link to specifically the F tables. And so what I can do here is just go ahead and pull this up just so that we can um, look at this together. Pull the distribution tables. All right. And so this first distribution table is this PDF document here. So we go ahead and click on that. We'll be able to see the F distribution table as this PDF. So when we look at this particular document, we're going to be looking at the numerator and the denominator degrees of freedom values. So the degrees of freedom for the numerator is going to be that k-1 value. And so you're going to be using whichever column represents that particular number. And then here on the left-hand side will be your within subjects degrees of freedom. And specifically in this table, you'll notice that the boldface values represent the 0.01 level of significance, and the table in lightface type are 0.05. So for instance, if you had degrees of freedom for 3 in the numerator, and then let's say 12 in the denominator, you would utilize this value here if you were testing at 0.05, and you would use 5.95 if you were testing at 0.01. Now, if we go back to our general page, there is another table that I have provided for you in terms of statistics tables. And let me go ahead and find that table here. And this is a site that takes you to the additional F tables website. Okay, let me just make sure that I'm sharing this fine, which I am. So this F distribution table is going to be broken down by the alpha that you are investigating. So for instance, if you scroll down here, this is the F table for an alpha of 0.05. So if this is the value that I'm asking you to test your hypotheses for, then DF1 in this table here is going to be your numerator degrees of freedom. That will be the column that you use. DF2 represents the degrees of freedom for your within subjects, meaning for your error or residuals, and you're going to see where those values intersect. So for instance, 3 down to 12, we have a value of 3.4903. So 3.4903. And if we look here at this F distribution table, back to this PDF, we have 3 down to 12, 3.49. So that aligns well, right? This particular website will take the values out to about 4 decimal places, which sometimes is a lot, but the general values are going to match, okay? All right. So that was the question that one student had specifically in terms of clarification on the F values. So hopefully that clears that up. Another student asked about specifically non-parametric statistics. So specifically when we're looking at chi-square, they had mentioned that in one of my slides, I had said, when the test is significant, we mostly speculate as to which observed frequencies were different from the expected ones. And so let's break down what that means. So remember that in chi-square, we're looking ultimately at nominal variables, which are categorical in nature. And so let's say, for instance, that we had favorite color, and I'm wanting to see if there is a preference for favorite color. So we have red, green, blue, and yellow. Okay. Remember that in chi-square, all we're looking at are just observed and expected frequencies. That's all that we're looking at. Now, in an ANOVA, if we have 4 different groups, right, and we get a significant F value, we can run a post hoc and specifically say which groups are greater than or less than another, and we can say which are significantly different. But in a chi-square, there are no post hocs in chi-square, meaning that if we have a significant chi-square value, then all we can do is take a look at our observed values, and we can just comment on which of those groups seems to be more chosen, selected, preferred, etc., right? So that's what I mean on slide 15 of chapter 14. When the test is significant, we mostly just speculate as to which of the observed frequencies were indeed different than the expected. Because again, when we look at the formula for chi-square, the greater this difference, the more contribution that is going to be serving in our overall chi-square test statistic. So for instance, if we have 100 people and this is even, expected would be 25 each. But let's say that red is 20, green is 20, but then blue is, let's say 50, and then yellow is 10. Now the observed add up still to 100, but notice that there is a pretty big distinction here in these groups. So if this was significant, which I probably expect that it would be, all that we could say is, in looking at this sample of individuals, blue and yellow showed the biggest difference between what we would expect and what we physically observed. Many more students chose blue as their favorite color, and far fewer students chose yellow. That's all that we could really do in terms of just speculation. Because again, there are no post hocs that we could do in chi-square like we have done in ANOVAs. Someone said that they're feeling a little bit nervous about the final. I definitely just want to encourage you to take your time with it. The final will open up and you will have at least 3 solid days. It is a cumulative final, meaning that you are going to be using and being tested on information that we have covered throughout this summer semester. So just please refer back to your notes, to all the videos. If you are able to identify what problems and what statistical problems we're going to be doing, feel free to consult those notes and refresh yourself as you're working through them. Someone had said the difference between goodness of fit and test for independence. So again, a goodness of fit test is going to look at one nominal variable that has 2 or more levels, so 2 plus levels. And then your test for independence is where we have 2 nominal variables. We can create a contingency table here. So let's say male and female, and then favorite color, red, green, or blue. And we can assess whether there is a relationship between these 2 variables. So again, ultimately, chi-square still just has to deal with counts. So when we're talking to someone at, let's say Mercer, if you're a male that likes the color green, you belong into that box there. And what we do is we accumulate those counts and we assess whether there is a relationship between variable 1 and variable 2. And then the last question that somebody had was looking at calculating a two-way ANOVA and just having more information on that. So in general, what I can say is that, when we're computing an ANOVA, ultimately the end goal is to come up with an F ratio, right? So the F ratio is the variability between our groups divided by the variance within our groups, right? And so that within group variance is known as error. Now, in a factorial ANOVA, a two-way ANOVA, we have 2 independent variables. This means that we're going to get a main effect of variable 1. We are going to get a main effect of variable 2. And when we say main effects, right, this is when we say that we are collapsing across the levels of the other. So if I just draw something pretty simple like this, let's say we have exercise as my first factor, and I have no exercise and exercise. And then let's say I have gender, we have male and female. This leads us to have 4 total groups: male, no exercise, male exercise, female, no exercise, female exercise. So if we're looking at the main effect of exercise, ultimately we're trying to see what is the average value between those who are in the no exercise group and the exercise group. We're comparing specifically these 2 groups for our main effect of exercise. Now, again, it doesn't matter whether you're male or female. If you're in the no exercise condition, you did not receive exercise. And so this column here represents no exercise, or level 1 of the exercise variable. This column here represents exercise. This level specifically collapsed across the level of the other thing. Now, we're looking for the main effect of the second variable, gender. We're saying, is there a difference between male and female? So the mean of males, is this mean different than the mean of females? Now, using just a different color here, again, I can say level 1 of gender is male. It doesn't matter whether you're no exercise or exercise, you're still male regardless. And then here in the second level of gender, we have female. So these are what we refer to as the main effects, right? So the main effect of gender is comparing male versus female. The main effect of exercise is comparing no exercise to exercise, right? And then in a factorial ANOVA, we have an interaction between the 2 that we have to test for. So this is going to lead to an F value that will allow us to decide if there is a main effect of factor A, another F value for factor B, and another F value for the interaction. Now, when we're doing these calculations, we always start with our sums of squares total, which is our sum of x squareds minus sum of x's squared over n. And this is something good to start with because we know that the sums of squares total is going to be broken down and partitioned into sums of squares for that first factor, sums of squares for the second factor, sums of squares for the interaction, and then sums of squares for the error or the residual. These all are going to add up together to give you that sums of squares total. Okay. So if we move this down a bit, your sums of squares total is solved here. When we look at our main effect sums of squares, we have sums of squares of, let's say, A is equal to the sum of x sub k squared over n sub k minus sum of x's squared over n. And so when we break down this portion here, sum of x sub k just means the sum of x's in each of those specific levels. So if we go back to our example here, our example above, there are 2 levels for exercise, which mean that we're going to get the sum of x's for the no exercise condition. And then we're also going to get the sum of x's in the exercise condition. Once we have the sum of those x's, we square them and divide by n sub k, so the total number of people in each of these conditions. Once we have that sum, we can then subtract sum of x squared over n. Okay? Now we can do that for the second factor. Sums of squares for b is equal to sigma x sub k squared over n sub k minus sigma x squared over n. And so this will just be regarding the second factor. So the sum of all the males, sum of all the females, right? Now the interaction is similar to this in terms of its calculation. So the sums of squares for the interaction is equal to the sum, but now we're looking at the sum of x for each of the cells squared over n sub k, specifically in that particular cell, minus sigma x squared over n. But when we're solving for the interaction, we must also subtract the sums of squares from A and B in order to get that interaction. What's nice is that once we know the total and we know the sums of squares of A, sums of squares of B, and the interaction, subtracting all those from the total will give us our sums of squares or error. Now, once we have our sums of squares, we know how to solve for variance, right? When we solve for variance, that is simply just sums of squares over degrees of freedom. So our sums of squares of A divided by degrees of freedom of A, right, would give you the variance for A. Sums of squares of B divided by degrees of freedom of B would give you the variance for B. Sums of squares for the interaction divided by degrees of freedom for the interaction would give you the variance for the interaction. And then your sums of squares for error divided by degrees of freedom for error gives you the variance for error. And when we're looking at our F ratios, our F ratio is again variance between our groups divided by variance for error. So here, variance of A divided by variance of error would give you the F value that would allow you to test the hypothesis for factor A. Same thing for B and the interaction. And so factorial ANOVAs are definitely a little bit more calculation heavy, but they do follow the same really steps, logics, and procedures as we've seen with the other ANOVA designs. And that is pretty much the end in terms of what students had questions about. We've wrapped up all of our main topics for the semester, and now it is just the end where we're working on our final exams as well as finishing up our final paper.